Good day, everyone. I am Regine Gonzaga Estanio.
And I am Godopher Nathaniel Claribto, and we were gonna talk about the introduction to the engineering.
Well, before everything else, what comes to your mind when you hear the word engineering? Well, for me, I think about invention, designing, building, and great thinking. Now, what does this word really mean? Engineering is the application of science to the optimum conversion of natural resources to the uses of humankind. Moreover, it is defined by the American Engineers Council for Professional Development as the creative application of scientific principles to design or to develop structures, machines, apparatus, manufacturing processes, or works, utilizing them singly or in combination.
Furthermore, according to Slow Foundation, engineering is the application of science and math to solve problems.
Did you know that the term engineering is derived from the Latin words ingenium, which means cleverness, and ingeniare, which means to contrive and devise? Products of engineering can be found everywhere, improving the ways we travel, communicate, entertain, and many more. Engineers indeed improved the state of our world and made our lives easier and safer. Now let's have a capsule history. Before the term engineer or engineering was used, there are traces in the early Roman times that they used the Latin expression ingenium to suggest the ingenious attributes of an object or a person. And eventually, its derivative ingeniator was applied to a person possessing an innovative mind and skillful hands in the making of such devices. And it was just 400 years ago when the word engineer became a substitute for ingeniator and it gradually appeared in common use. But even before Romans named those clever and dexterous individuals as ingeniators, innovative artifacts and devices had already emerged during the earliest stirrings of human imagination. They built tools and devices to better suit their wants and needs since before recorded history. Since then, systematic progressions in the world of engineering are evident, from the prehistoric making of stone tools to the building of ancient pyramids, from medieval construction of cathedral and fortresses to the intricate crafting of mechanical clocks and movable type printing. From the isolated discoveries of glass lenses and iron casting to the development of tower mill and steam power. From automobile assembly plants to modern jet aircraft manufacture and more recently to deep space probes and microchips. Today, engineering is a highly technical and continuously evolving academic and professional discipline taught at universities and polytechnic institutions. Now let's move on to the core of engineering. The innovative Roman engineers were evidently engaged not only in tactile actions but also in cognitive process. Engineers must think about the properties of natural materials, consider the devices for specific purposes, proceed to trial and error, and of course, learn from their failures. This is a model of an input-output process of creating an ingenium or to yield a device of a particular utility. The natural materials or the materials and their properties are studied and imaginatively shaped and assembled by engineers with a rectangle in the diagram which suggests their creative thoughts and skilled actions which results to the building or making of an ingenious and useful device. This symbolic depiction can also be used even for Stone Age man. The natural stone, which is the material, was shaped and assembled by the humans, which are the engineers, through stone chipping, which resulted to the development of stone tool, which is the ingenium. This representation can be written like this: the nature, which are the materials and phenomena, shaped by the thoughts and actions applied in engineering, which results to the making of the devices which are both ingenious and useful, and can be further compacted into NT shaped by ET, which results to DT. We have T or time as the pervasive variable since the workings of engineer vary according to time. And now, let's move on to the symbolic notation and engineering. Earlier, conceptual constructions and associated notations of particular relevance to engineering in time was introduced. The symbolic notations is important and useful in our context for these three reasons: familiarity, empiricism, and heuristics. First is the familiarity. Symbolic notation represents aspects of thoughts and actions in graphical form which help students of all engineering disciplines to familiarize the context easily. Second is empiricism. Symbolic notation constitutes a practical way of depicting complex processes of central importance to the theory and practice of engineering. Third one is heuristics. Symbolic notation suggests useful and efficient means of organizing and exploring historical progression and contemporary context of engineering. There are many forms of notations, and the following are some of them: force diagrams, circuit representations, electromagnetic field depictions, vector notations, and phase plane projection. In engineering, symbolic and graphical notation has long proven to be a most effective and powerful instructional and operational tool which gives a valuable cognitive focus for complex physical phenomena and processes. It helps engineers to easily understand such things.
Essential components. NT represents nature as the basic starting point for most relevant progression. In nature constitutes the resource of the basic materials essential to the practice of engineering, like stone, wood, and fiber. Nature embodies the physical phenomena of foundational importance to the theory of engineering, like hardness, diffusion, and heat. Nature possesses autonomous dynamical features of relevance in the performance of engineered devices, like earthquakes, water cycle, and hurricane. Nature may induce a transcendental sense of engagement, and it may also stimulate a depth sense of place attachment. The term DT identifies engineered devices. It is the ingenious and useful human-made object that has been judged by common pragmatic criteria. Under with this term, a device may be an artifact, constructed or adapted, but invariably based on considerations of synthesis. It may be hardware object or interactive machine. It may be cognitive object, such as a strategic idea, optimal process, and action program. A device may be associated with a commodity, providing selective functions, like projection of information, means of transportation, serve the needs of sustenance, supply the entertainment, and provide physical comfort. A device may also be characterized as a synthesized object which engages, stimulates, and enables its makers and users. And a device may be further be viewed as a convenient unit of engineering theory and practice. With nature and identified engineered devices, it is evident that engineering, or the term ET, constitutes the central and uniting connection in the progression from NT to DT. Engineering represents creative thought and skilled actions associated with the use or adaptation of natural materials and natural phenomena in the conceptualizing, planning, designing, developing, manufacture, testing, implementing, improving, and disposing of devices. Note that these characterizations evidently define engineering not only as a creative activity, but also as a goal-seeking activity. For what we discussed earlier, it is part of the Table 1.1 that provides a summary characterization of the primal, as what you can see on your screen. So let's go to change in engineering. All contemporary professions need to consider change and describe change in terms which are specific to their interest. For engineers, the term progression is especially informing in the characterization of some important changes in their work. So there are 4 classes of progression that we will discuss this day. First, the homogeneous progression. Homogeneous progressions describe the magnitude of a time-dependent variable which is associated with some device or devices. Note that in a homogeneous progression, each term possesses the same units. So consider this illustration that an aircraft cleared, takeoff, as what you can see on your screen. So it starts with 0 speed at time, to intermediate speed at a time, and lastly to takeoff speed at a time. As another illustration, the sequential changes of the mean temperature in a reaction vessel in the process of startup or shutdown may be represented as what you can see on your screen. These two examples represent homogeneous progressions and involve some specific measurable variable. The term is xt at successive time coordinates. So, in complete generality, we may write for such changes in time like this on what you can see on your screen. Second, the heterogeneous progressions. The heterogeneous progression is no comparably and explicit defining expression. Heterogeneous progressions display the contingent role of the human imagination in community preferences. And the practice of engineering involves many informing progressions which are not fully describable by one homogeneous variable. So consider the following historical example. As you can see from different historical examples, it starts with early age technology or devices to more technological advanced devices. For example, the historical progression of clock. It starts with shadow clock, wherein our ancestors used their shadow to determine the morning, noon, and night. And it evolves to water clocks, to weight-driven clocks, to pendulum clock, and to the current annoying clock for bed lovers, which is the spring clock that we usually call alarm clock. And the distinction to the general form of homogeneous progression, it can be written in the general form of as what you can see on your screen. Note also that what actually flowing in heterogeneous progression is a combination of forms of matter, energy, information, ingenuity, and authority. And also, it is increasingly essential that engineers think in terms of heterogeneous progressions for such invariably characterize important aspects of the practice of engineering. So let's go to the third progression, the primal progression, a very special meaning to the family of heterogeneous progression was assigned here in the primal progression, which is the 3-note progression represented by as what you can see on your screen. Then we already discussed it in the essential components. The primal progression embodies a unique evolutionary past and contingent future, establishing thereby a distinctive temporal complexity to the evolution of engineering. Engineers need to understand the related past for their creative thoughts and skilled actions become operational in the future. Last, or the fourth, the connectivity progression. Connectivity progression expand the primal progression by adding additional terms that suggest processes such as feedback, forward, recursion, and branching. For example, like this. Yes, the 3-note progression can be added with additional terms and additional system, and that is the connectivity progression. So let's move on. Sana all maka-move on. So let's go to engineering and time. Engineering has, over time, become increasingly identified by association with classes of devices. Civil engineering has or with civic devices allows the civil engineers to help local area, city, town to solve environmental issues and structures. Mechanical engineering with their mechanical devices, chemical engineering with their chemical processing devices, and the electrical engineering with electrical or electronic devices, and so on. These devices undergo with different processes, and we can illustrate it using the primal progression. As what we can see, the three-node progression has been added with I and J. The I is the time-varying workings of an engineer, with engineering discipline in making of ingenious J-type devices. The J-type devices, or DIJT, emerge from a broad historical context and relate to conceivable engineering projections about the future. To highlight this creative and goal-seeking feature of engineering, this is the illustration. As what we can see, DIJT is expanded with historical evolution of devices, which relate to and predate that occurs a date earlier than DIJT, and expecting for continuously future development of devices, which relate to and post date that occurs a date later than DIJT.